Welcome everybody to the Qt Embedded Days 2021. I am Giuseppe D'Angelo, and in this very short talk, I would like, yes, indeed, to demystify C++ a little bit for C developers. As Christopher just said, so who am I to talk to you about this? I am a software engineer here at KDAB. I'm a developer. I write a lot of C++ code. I'm also a trainer. I try to teach C++ to people and try to understand what kind of background they come from and what kind of challenges they encounter when moving from other languages to C++. And in the embedded world, C is, of course, the strongest language out there. It's not just something that I say, it's what market research says all the time. And so the point of this talk is going to be how can C developers move to C++ without struggling into the transition. There's much more than meets the eye here. Okay, so let's take our time. Let's discuss exactly what's going on there. So let me start from this very simple observation. I just stated a fact. I just stated that C has been much more popular than C++ on embedded systems. Is it actually the case? Well, all indicators say that yes, this is the case. I've done a little bit of research and looked at the last statistics from the IEEE surveys, from the embedded.com surveys, and from other similar resources that you can find online. And pretty much since forever, C++ usage on embedded devices has been behind C usage. I got a couple of statistics just here, just to show you some of these data sources. For instance, the IEEE Spectrum top programming languages for last year shows that Python is the most popular language amongst embedded developers, followed by C, followed by C++, and then followed by others, generally assembly or specific programming languages like Arduino. And if we look at these as a data series, even in the past few years, C has always been on top of C++. So there's never been a moment, except this little moment here in 2018, where C++ has been more popular than C. And as a C developer, this kind of hurts me and makes me raise the question: why is that? What's going on here? And uh, why do these graphs look like this? So why is that? Is perhaps C++ simply not available for some developers? That is a good question. Sometimes when we deal with C++, we deal with compilers, and especially in embedded, not all vendors provided, at least historically, a C++ toolchain. Or maybe they provided one, but it was outdated and bugged. Luckily, this is no longer the case. In the last 5 years, at least, I've never encountered the case where you got a board of some sort and you had a C compiler for it, but you also didn't have a C++ compiler for the same board. There is a good trend here, which is finally vendors are starting to move towards standardized solutions for their compilers. They're stopping reinventing their own compilers. And so once you have compiler like by GCC or by GNU, then you do have the possibility of running C++ code. Is perhaps C++ just not suited for embedded development? It could also be the case, right? For instance, does it perform too poorly compared with C? And so when people have the choice, then they go to C. Maybe it does not offer the same good qualities of C++. I don't think so. I don't think that this is the case. C++ as a language has been designed from the bottom up to be as performant as it can. You remember the don't pay for, don't use paradigm of C++. And in general, C++ is always used in all the contexts where you want the maximum performance of the system. If you look at large, anything today that requires fast code is realized using C++. Video games are done in C++. Banking software is done in C++. So the fact that C++ might be slower than C just does not match the expectations, right? And if you ask around, if you ask any C++ developer, they will tell you this is not the case. C++ is better than C at all in all metrics. So it's not a matter of quality. It's not a matter of technology here. Maybe is it just the case that C developers don't like C++? Okay, I think we're getting there somehow. Why don't they like C++? And what are the particular points that make C++ so unpleasant to C developers? Is there anything that we can do as C++ developers to make the transition easier for them? Can we simplify things when they may need to be simplified? Can we remove the parts of C++, or can we hide the complexities away so that people are not scared by C++ development? Well, maybe we can do something there. But in a nutshell, what I'm trying to say here is that the poor adoption by C++ of C++ by C programmers is not a simple one-dimensional problem. There isn't just one thing that we may need to fix. And most of the time, it's not a technological problem. C++ is not worse than C from a technology point of view. However, we still encounter a resistance there. And that resistance, not being technologic, what is it about? It's usually human. Yep. Remember this when we deal about advocating how big and good C++ is to a C developer. For the majority of developers out there, programming languages are simply a tool to get the job done. They don't look at C or C++ as something interesting per se. They don't like do language research or something like that. They need to deliver a project. They need to deliver a project according to the specifications on time within the allocated budget. So maybe they just cannot afford spending time and learning a new tool. They are within their comfort zone by using a tool that they already know, they already mastered a tool. There is no need for them to change at all. And this somehow impacts this decision, because if there is no incentive for people to change from C to C++, then why should they change? Why should they do the move? Yep. And just for a second, ask yourself, what happened if tomorrow I come to you and ask you, please do a new project in a different programming language, one that you're not totally familiar with? This means, again, shifting people out of their comfort zone. And shifting people out of their comfort zone is a huge demand. It adds a lot of stress on people, and people are not willing to do this at all, in any case. And the interesting part for me there is that this is not just something that we do in technology, in IT, when programming. This is just a general fact of life. People like their comfort zone. People don't like to be pushed outside these boundaries. And in order to go there, they need really, really strong motivations. Sometimes even looking at seeing that there are some advantages at moving to C++ is nowhere not enough. They will need much more motivation, such as you need to understand what are the disadvantages at still using C in 2021, and then understand, okay, why moving away from a language like C is probably a good idea today. And just to give you a data point, if I am a C developer and I look at C++, the sheer complexity of C++ can scare me off. So even seeing what are the advantages of C++ is not so obvious. If we take a look at the sides in number of pages of each published C and C++ standard, the latest C++ standard, C++ 20, stands at over 1,800 pages. The latest draft of the C standard is slightly more than 600 pages. So yes, C++ contains at least 3 times the stuff which is currently in C. How can I possibly master all of that? How can I possibly jump over there and understand what I'm doing? Yes, that's right. That is a scary prospect for everyone. And so people don't like this idea. They are scared and they will bounce back within their comfort zone. And this is a nice thing that led me to a nice realization here, because when you push people around, people are facing this hard to explain complexity of C++, what is the first thing they do when bouncing back? They invent stories, right? They invent myths, they invent legends. They try to exaggerate something that in order to, if you want, justify their behavior into staying within their comfort zone, right? For instance, the first thing that people might tell you, yes, go ahead, use C++, and after a few days, you will find code like this. You will start facing write-only code that you can write only once, and then it's just complete mess, and you will not be able to find your way outside of that. Guess what? This is a complete myth. It's a complete fabrication, right? There is no need of going there unless you need this stuff in C++. And nobody will force you to use this complex stuff unless you want to. Yeah, especially when coming from C, you don't need to do any of this. How do we call these myths today? Today, we don't call them myths. Today, we call them fake news. And just a few months ago, I encountered a very nice quote by a historian here in my own town that explains the origin of fake news. Just 100 years ago, writing about the First World War, this historian, Mark Bloch, wrote about the origin of myths and false news in the context of war. But what's great about his observation is that this observation tells us that all these stories, all these myths, have a common origin, and the common origin is reassuring us, is perpetuating our preconceptions, are perpetuating our prejudice, making our fears alive through the myth. Yep. The quote says that false news have a seed of truth. They're born of imprecise individual observations. So yeah, code like this one does actually exist. Yep, this is the seed of truth within the meat of C++. But the actual fact does not explain much. It explains really nothing. Then what happens is that once this news is born, this error propagates itself. It finds its own life and eventually survives, provided that it finds a favorable cultural growth in the society where it's spreading. So the community of C developers who see this stuff in C++ and say, okay, that's scary. I don't want anything to do by that. Oh, have you seen that code over there? However, where is the moral? The moral is that through the myth, people express their prejudices, their hatreds, their fears, and all the strong emotions. So it's really hard to overcome this, but it's very important that we realize that this process does exist, and it exists probably since the origin of mankind, and it will stay with us for a very long time. The best way that we have to fight this is to recognize every time we see some sort of fake news that we are involved with it. Fake news are building, are really thriving out of our own emotions. And so we need to try and put emotions out of the picture, as hard as it sounds, because we're still human beings, if we want to address this, if we want to actually have a solid conversation about the pros and the cons of C++ over C. And before you say, but wait a minute, we are software engineers, we are scientific people, we shouldn't do this, right? We don't do this. No, that's not true. We do this all the time. I mean, I don't want to start a flame war about Emacs versus VI, but if you have done, if you've ever been there, you know that people try to do this. People find their own tribes, and people mock the adversary using any weapon at their disposal. Because we're human beings, we work like this. And being software engineers does not make us special in any regard. On the contrary, it makes us even more exposed to some of these phenomena. So how do I make C++ better for C developers? I still don't fully know. Okay, I have a few ideas. And in this talk, I'm going to explore a few ideas. But my best advice to date, up to now, is this. If you are a C developer and you want to start exploring C++, you want perhaps to start improving your code base by adopting a little bit of C++, I would strongly suggest you to start by using simple things. Okay, don't think of just jumping into super complicated C++ because that will not make you a favor. So, for instance, let's try and identify simple programming patterns that you can fully control. Okay, maybe they are perfect replacements of things that you have already been using. Yep, and you can start already getting confidence by using those. You can already improve your usage of C++ by start sticking to simple things. In a nutshell, if the complexity of C++ is daunting because it's so big, try to focus on a limited subset of C++. And I know so many people what are screaming right now in the chat. They're saying, but using a subset of C++ is not using C++. I don't care. To me and to most people, programming languages are tools to get the job done. If you can get away by using a small subset, that's fine enough. Even doing blasphemy, using C++ as stupid classes, that is already enough for most people out there. At the bare minimum, you get some advantages out of that. You get proper syntax for doing OOP, you get destructors, you get inheritance. You can already do a lot of interesting stuff without the dangers of doing the same stuff in C. So now that we have established the mindset and the common framework, please let me use the rest of this talk to show you some appreciation of C++ features and hopefully debunk some of the false stories that you may have heard in the meanwhile. For instance, myth number one, if you want, C++ generates bigger code. So C++ is worse than C from this point of view. Yeah, maybe that's true. Maybe that's false. But just think about this. How wide is that statement? I mean, if I give you a sentence that C++ generates bigger code than what? What are the input conditions? Right? Maybe in some case it does, maybe in many other cases it doesn't. You can see this myth in action here, right? Just one seed of truth can get twisted and bent in a way that makes you believe what you already want to believe, right? But in general, this is not true. Why is it not true? It's not true because in C++, remember that you don't pay for what you don't use. And this is true even in terms of code size. C++ developers, C++ compilers don't just randomly increase your code size because they want to. To say it all, actually C++ compilers can optimize for size just as well as C compilers. There's nothing strange there. However, if you do use some C++ features, then you may find an increase in code size. The solution to this is don't use these features or actually disable the usage if you're not fine with this. What kind of features I'm talking about? Well, if you don't use things in C++ like exceptions or like runtime type info, then just pass a couple of options to the compiler to stop the compiler emitting the related code. This can shrink your code size to the same code size that you have in C, because now the compiler is not emitting anything special runtime support information to enable some specific C++ language feature. So in both GCC and Clang, you can pass these options to disable RTTI and to disable exceptions. Maybe your embedded compiler also has the same, or maybe your embedded compiler does not support exceptions to begin with, then all the better, right? You don't pay for any of that, and the generated code is equal than the one that you would generate when using C. So there's nothing to pay there. If you're not even using the C++ standard library, so if you really want to limit yourself to your custom code, no standard library involved, then you can actually not link to it. And this will further reduce the code size because you don't need to ship the standard library along your program, right? Or if you do static linking, then the standard library is not going to be included inside your application. How do we do that if we want to? If we want to do that, for instance, when using GCC and Clang, we can ask them not to link against their respective default standard libraries. In fact, the standard library that ships with GCC, which is called libstandard C++, and the standard library which ships with the Clang, which is called libc++, they're both made of two distinct components. libstandard C++ has an internal library called libsup.c++ or support of C++, and libc++ has a smaller library called libc++ API. And if you really want just the bare minimums that is required to run a C++ application, you can link to these two smaller libraries and not to the respective standard libraries. This can give you a significant advantage in terms of code size. Actually pulling this off is a bit tricky because you need to actually use GCC and not Clang to perform the final linking step. By default, G++ and Clang++ will link to their default standard libraries. But you can do this. It's very easy. You just do it once in your build system. And now your code size has been shrunk even further. And another thing you may want to do here is to limit the usage of templates to, if you want, fight a little the possibility of having a code bloat. When you use templates and we instantiate them, templates may generate more code, again, compared to what? Compared to possibly generic solutions that you are already familiar with when using C. Now, the reason why they generate more code, if anything, is speed. C++ may decide here to trade speed for code size. But once more, no one is forcing you to use them. If you already have C solutions that expand to very little code and are extremely optimized for code size, then keep using those. No one forces you to use templates. Now, of course, why do we use templates then? Well, there are good reasons. Templates are more generic than the equivalent C functions. They can perform more type checking, so they can be more correct than a 100-year-old C solution, but they're not mandatory to use. So if you cannot afford them, just don't use them. Yep, you can still keep the code size under complete control. So lesson learned here, right? When people tell you code size is a problem in C++, it just depends. It's not it's not false, but it is definitely controllable. So the myth that is born from there grows out of dimension and make people bounce back in their comfort zone of C development rather than actually trying a little bit of C++, measuring how much code is generated, and then deciding for themselves. Now, it's not the only story here, of course. For instance, C itself can be pretty ugly in some of its usages. And C++ can beautifully solve a lot of the superficial problems. And once more, when we do this, people start saying, okay, what I'm paying here, there's hidden magic. There is something that you're not telling me. There's nothing I'm not telling you. Okay, and I want to show you this. About some ugliness. Yeah. Let's take some C99 code. Now, C historically does not have overloads, meaning that suppose that you have different functions that actually do the same thing. They are different functions simply because they act on different arguments. So in the C standard library, the function that calculates the sine of an angle is called sin right here. And the sin function takes a double argument and returns a double. But what happens if you have an angle which is a float? Then you have a different function called sin f. And you have an even different function called sin L if you have a long double. When you need to call one of these functions, you as a developer are required to know which one to call. Yeah, so if you have a double, you call sin. If you have a float, you call sin f. You can even do it wrong and accidentally use the double version on a float. It will still work. Yep. But it sounds like a mistake that you may do here, but yes, it is a mistake, and C does not help you there. We cope with this complexity by remembering a lot of patterns in our mind, and remembering that every time you call a given function, for instance, on numerical arguments, you need to check its overloads or your pseudo overloads and always use the right suffix for the right overload. This adds a lot of mental burden because it's so easy to just forget about this rule and maybe, I don't know, accidentally call the double version when using a float. That will just work and you will not notice the difference typically. Now, C itself tried to solve this problem. Raise your hand, well, virtually at least, if you've ever seen a code like this. Yes, this is a legal C code. It's legal C11 code. In C11, there is a new macro, or well, a new functionality of the language, which is called a generic. And a generic allows you to pretty much write a dispatcher macro that, taking an input, will dispatch it to a different function depending on the type of the input. So you still have your three different sign functions over there: sign, sign F, sign L, because C does not have overloading. And then what you do is that you define this generic macro, okay, that takes an angle, and if the angle is a long double, then actually calls sign L. If the angle is a float, it calls sign F. If the angle is anything else, sin. Okay. And now you can actually use the macro, so the same named function, to call the first one, to call the one for double, the second one to call the one for float. That's fine. That works, and that's great. But this looks awful. How many people actually use this? I hope not that many people, because it really, really looks bad. Yeah, I mean, this syntax, yeah, it's syntax to copy and paste from Wikipedia, but you can live with that, if I guess. It just looks like a workaround for a language problem. And needless to say, C++ has always had overloading without any awkward syntax. In C++, you could always do this since forever. Yep. So which one is better here? Is C++ better than C, or is C better than C++? Well, the danger of accidentally calling the wrong function because you forget the suffix is there. I myself have done it countless times, and perhaps so have you. So why using the suboptimal solution, right? Just use C++ for this single feature, and your program will already be slightly better than before. Yep. Now, let me elaborate on this, and let me continue on this journey. In C, you are already probably doing object-oriented programming. Yeah, there isn't a specific syntax of or object-oriented programming. It's really what you do that defines whether you're sticking to that pattern or not. So if you use C, maybe you have used code that looks like this, right? You create an object, or well, you just declare an object from set point of view, so pthread mutex. Then you use a construction function, such as pthread mutex init, to actually build that object. Then you call functions that take that object as parameter, yep, to operate on that object. And once you're done with it, you destroy it. You call another function, such as pthread mutex destroy, to destroy that mutex. Every C library out there has code that looks like this. Okay, this is from pthread, but if I look just elsewhere, for instance, into glib, if you have to use glib and you have to create a string, how do you create a string using glib? You use gstring new to create a new gstring object. You call functions on these gstring objects, for instance, such as gstring append or gprint. And once you're done with it, you call gstring free. Yeah. Everyone does object-oriented programming in C, and everyone does it using syntax which looks like this. So why not doing it with a slightly more convenient syntax? In C++, the equivalent code would look something like this. Create an object of type mutex, and this builds the object, and then you call lock and you call unlock. Yep. This stuff is exactly the translation in C++ of this code on the left. It does not cost you more, it does not cost you less, it costs you exactly the same. It's, if you want, syntactic sugar. Uh, Apart from the specifics of locking and unlocking a mutex, the semantics of this, the code that the compiler will generate in order to implement this lock function and this unlock function is actually the code on the left. A function, a method in C++ is simply implemented as a function that takes a pointer to the object as the first argument. It's just that you don't see that argument right there, but it's there when the compiler implements this. So we're just basically switching from a slightly more verbose and awkward syntax made of three functions that take the object to operate upon as the first parameter to another, more convenient syntax where you got an object and you call functions on that object. Under the hood, they are exactly the same and they cost exactly the same. And you could say the same here and here. So if you use a class from Qt called the qbyte array rather than just string from glib, then you can create a qbyte array, you can append a new string into it, and then you can print it using printf. This is once more exactly the same as what we did before, just using a proper syntax. There is something else magic about this in here. In particular, in this code on the right, there is something missing respecting the code on the left. What's missing? Well, did you see that I didn't destroy anything? Did you see that the calls to the instructions were missing? Yep, that's right. C++ does this for us for free. Local objects, that is in C++, when you destroy a local object, in C++, when you walk out of a scope, the local objects in that scope get automatically destroyed. There is no need for you to do anything. Yep. So I go back one slide. What happens if here on the left you forget about one of these destruction functions? That is a problem, right? You're leaking some sort of resource. And this is very, very annoying because it puts mental burden on you. You need to remember every time you see a construction of some sort, an init function call, a new function call, you also need to immediately think about, okay, who's going to call destroy on my mutex? Who's going to call free on my gstring? In C++, there is no such need of that because when you destroy the mutex object, that's going to destroy the underlying mutex. When you destroy the byte array object, that's going to free memory. And that is completely automatic. No need to remember anything. So many errors don't even manifest themselves in C++ because of this important feature. And what's even better, each class can define what to do when objects of that class get destroyed. So a class that holds memory can decide to release that memory. A class that holds a mutex can open that mutex. A class which is a socket connection can disconnect that socket connection. All of this happens completely automatically, and that's one of the most fundamental C++ features that are so dreadfully missing from C++. I believe that entire categories of errors would never manifest themselves at all in C++, in C, sorry, if C had some sort of features like this one in C++. And to show this feature in action, let me show you some code from a random project that I want to mention right here. This is C code. And suppose that you have a piece of code where you have to do several operations before actually doing work. For instance, you enter this function. The first thing you do is that you try to allocate some memory. Okay, now you don't have, if the memory allocation fails, then you want to bail out of this function. Okay, and there is a mysterious GoTo there. I wonder why is that? Well, we'll go to that in a second. Then the second thing you want to do is to open a file. Okay, so you call open, and if open fails for whatever reason, then you also bail out, go to another error2 label down here. Then you lock a mutex. Okay, then now you have all the resources to do your work. Perfect. And now that you've done your work, what do? Well, we need to undo the work done so far. So we need to open the mutex, close the file that we have opened, free the memory allocated in the buffer, and then eventually return the result. In any big code base, any C code base, this is the pattern that you will find in there to deal with the possibility that you may have several errors raising from within one complicated function. And every time you face an error, what you need to do is that you need to undo the work done so far. And that's the reason for these gotos labels down there. These gotos will make you jump to a corresponding piece of code where you undo the work done so far. And since you need to undo that work even in the success path, so when you do the work, the result is good, and then you still need to close the file and undo and free the memory, you use labels like this to avoid code duplication getting out of hand. Okay, so this label right here, this R2, if you take a look, is jumping to a code path where it will free the buffer, so the thing done before it, and then eventually return. Yep. And each of these conditions has a matching condition at the tail. You see that for each acquisition, there is a check of sorts that jumps to the end of the function if that check fails. And the order in which this happen has to be exactly symmetric or mirrored at the end. So we first try to acquire memory, then we open a file, then we acquire a mutex. Then in order to undo this work, we release the mutex, we close the file, and we free the memory. Okay. This is how we do structured error handling in C since forever. Any big project adopts a practice like this. By the way, this is also the reason why in C you have the common mantra of having just one return path out of a function. How many return statements are inside this body? Only one at the end. And why is that? Well, because returning from the middle of this function would be a problem. It would mean that we are not releasing something and we're leaking resources. We don't want that to happen. So for that reason, people tell you in C to stick to the pattern of having just one return statement at the very end of the function. Before, put your put your code that deals with releasing resources, yeah, and build this structure of jumping to the corresponding path, to the corresponding branch, to the corresponding label, I should say, when something fails. So the question now is this code robust? Is this code because for certain this code is verbose as hell, right? You need to remember every time to do something to add a corresponding path at the end. Is it robust? So what happens if I realize that I also need to do something else here in the middle? Well, it will mean that I need to go carefully down at the tail and also add a corresponding check, a corresponding undo of the action. It needs to be in the reverse order of what I'm doing. It's not easy to do it right, and it's certainly a lot of mental burden again. Yeah. Now, in C++, all of these, as we just saw, works out of the box. It works out of the box because in C++, as I just said, when we destroy an object, that object can release the resources it's got allocated for itself. So the equivalent code in C++ for what we just saw may look something like this. You get a pointer to a buffer, and if you didn't get it, then just bail out returning failure. Nothing to do. Try to open a file, and if you didn't get it, return failure. Now, what happens in this case? Well, you're returning out of a function, and that means that you need to destroy this buffer object over there that you have just created. And destroying that buffer object is going to actually release the memory that you have allocated for it. There's no need for you to remember to do so. It's completely automatic and done by C++. And then what we do is that we acquire a mutex by using this other scope lock class. We do the work, and then we return success. And when we return success at the end, this return is going to destroy in order the lock, the file handler, and the buffer. So the order is exactly the one that we would expect. It's the opposite order of creation. And the opposite order of creation will ensure us that we are going to do exactly what we were doing in C, and also that is correct because There are good reasons for undoing work in the opposite order. And I believe that you're wondering, wait a second, is this code going to generate more bytes at runtime? Is the compiler going to compile this in a very strange way? Well, guess what? It's not. The compiler is going to compile this like this. The compiler is going to add a tail to your function that undoes things in opposite order. And these return statements are going to be compiled as jump to the corresponding label at the tail of the function, in which you undo just a little bit. So the implementation of this is going to be exactly the one that you had in C. And the advantage is that you don't need to do so yourself. And it's a huge advantage. Removing mental burden and having a way of automatic safe failure is a great achievement of C++. If you want to use C++ for just one feature, make it be this feature. Don't use anything else from C++. Just use the fact that you can define what happens when objects are destroyed. In C++, this has a name. It's called RAII, or Resource Acquisition Initialization. Fair enough. Call it whatever you want. I like to call it the ability of defining the structures is probably the most significant ability that you can find in C today. And now when we look at this code, we may realize something. That is, this function is returning failure or success, but C++ has a different mechanism to returning failures. If we want, we can decide to opt into exceptions and even remove the return path from this function and just say that this function now returns void. If you call this function and it completes, it means it does its work. But if something goes wrong, you may decide to throw an exception out of this function and so manage the failure by exceptions. This will simplify your code even further, and this will be correct. What is the trade-off here? The trade-off is that now you pay for this convenience. Okay, now you have decided to opt into the bits of C++ that will cost you a little more. For this specific piece of code, I've just done an experiment. So on x86, for this code, you're going to add around 100 extra bytes to deal with the exception handling code. Maybe some of these bytes are even shared amongst other routines. I don't know that, but certainly it's something that you may decide to opt in or opt out. It depends whether you can afford a little bit of cost added on top of your functions in exchange for even fewer lines of code to write and doing things by exception handling. Okay, so you can even reach this if you want to, but I'm not telling you to go here. And everybody who tells you to go here is lying. Now, where we talked about classes and in C and C++, and we talked about object-oriented programming in C and C++. Let me talk about inheritance in C and C++. This is also something that you are already doing today. If you are using C and you're using some libraries in C, many libraries allow you to define subclasses for their types. Take a look at this example from the left. This is an example actually coming from Qt, in which we are defining a subclass of the type gsource. Gsource is a type coming from glib, and the glib library, which is a C library, is telling you that if you want to create a subclass of gsource, what you do is that you create a struct and you put a gsource object as the first member of your struct. Other libraries will tell you, please put a macro as the first thing inside your struct. Other libraries will tell you, please decorate your struct in a given way. It doesn't matter what they tell you to do. What matters is the result here, because what's going on here? Why is C telling you to put a special member as the first one? It's telling you to do so that in memory, when this gets compiled, your object will have the source object as the first one. And this means that a pointer to the new struct that we have just defined is also a pointer to this source object. So if you have a code that needs to deal with your subclass, then you can pass the pointer to the entire thing. But if you have a code that doesn't care about your subclass and simply wants to access the base class, the source sub-object, then you can pass the very same pointer. You don't need to adjust this pointer in any way. You don't need to do anything because it's the same pointer. The same pointer points to both the source subobject as well as the complete subclass you have just defined. And how does this work practically? Well, that's when the fun begins because the type safety is still a little brittle there. In particular, in C, how do you get a pointer to your custom struct converted to a pointer to the base class? There isn't a way in the language, so sometimes all you need to do is accept a void star. Yeah, you take a pointer to your special subclass, you convert it to void star, or well, that conversion is implicit, and then you use that void star to pass it to the library. And you just have to swear to the library, yes, cross my heart, that void star I'm giving to you is actually a pointer to a specific subclass of the type you're expecting. But the language does not mandate that. The language will not save you in case you accidentally do it wrong and pass a pointer to something else, something wrong perhaps, not a subclass of the type. That's bad, right? How many bugs have you had introduced because of this? Maybe you did somewhere. I certainly did in the past. I certainly did when I used glib myself. Can we do better at this? And yes, once more, C++ has a slightly better syntax for actually doing the very same job. In C++, we would realize exactly the same thing, and I mean exactly the same thing, by using an explicit syntax for inheritance. So here I'm defining my struct, and I'm telling C++ this struct inherits from gsource. The generated code for this struct and the generated data structure are going to be absolutely identical. So in memory, I will still have an object which has a source subobject if you want, followed by my own data. And now the difference is one and one only. That is, the compiler knows that my object is a subclass. And since it knows that, the compiler may allow for certain conversions because it knows that they are perfectly legal to do. For instance, if I have a function that wants a pointer to the source object, okay, so I can mark that function to take a pointer to gsource and not void star, not any pointer. No, I can give you a pointer to gsource. And if I have a pointer to my complete subclass, like this object down here, I can still call fun passing the object. The compiler will allow this call because it knows that a pointer to my subclass can be converted to a pointer to the base class. I've written it in the very first line. My subclass and the base class are related. They are part of the same inheritance hierarchy. So even this little step here can give you type safety on top of something that you don't have in C. See, a type safety apparently don't really go hand in hand here. But wait, there is more. In glib, when we create a subclass like, again, when I create a subclass like my gsoctor notify source by inheriting from this gsource type, glib also tells me this, that if you want to customize the behavior of this source object, then when you create it, you can pass a table full of pointers to functions, and it's this gsource funcs pointer here. And this table will allow you to customize the behavior of this source object for your own specific use case. So glib tells us, build a data structure like this. Okay, put gsource as the first member. Then give me a table of pointers to functions like these socket notifier source funcs. Okay, and when you create this gsource object over there, you're going to tell me what this table is. So glib is going to remember these pointers. right? Somewhere inside this object, there are going to be a few pointers to these custom functions of mine that allow me to customize the behavior glib, which means that inside my object, I'm going to have pointers to functions. And when the glib needs to do something, it's going to access the object, follow the pointer of this function, and call my customized function to do something. Well, congratulations, because you have just invented or you have just implemented virtual functions in C. This very same mechanism exists in C++, and it just exists with a, if you want, good syntax, a better syntax than this. In C++, had the glib been written in C++, the equivalent would look like this. You get your struct inheriting from gsource, and then you write your functions, marking them as overriding the same functions defined in the base class. This code will get compiled in something which is extremely similar to the one that we just saw. That is, the compiler inside my object is going to put a pointer, but this time it's not going to be a pointer to the function itself directly. It's going to be a pointer to a little intermediate called a virtual table. And this virtual table for my custom subclass is going to contain the pointers to the target functions. Now, this virtual table in the middle looks like it's adding a layer of indirection, and this is going to cost you. Well, if you want, yes, this is going to cost you an extra function, an extra jump from the object to the function to call. So you may think of that this is a disadvantage, but this virtual table will also save you something, in the sense that there is only one virtual table for the entire gsocket notifier source class. And each object now has got only the room for one pointer inside of it, rather than many pointers from within the object, right? All the object needs to know is where the virtual table is. And that is, as data structure, you only got one instance of that data structure in memory. And then this virtual table is going to point to the actual functions to call for this specific subclass of gsource. So the cost at runtime might be slightly a tiny bit worse than what you pay in C, but the convenience of this is immense, because this syntax is now easy to read. You don't need to build tables of pointers to functions. You don't need to make extra sure that these pointers to functions are indeed the ones that you meant to use and not some other function that was not supposed to be there, and so on. Yep. And now, since I'm probably running out of time, just last but not least, another couple of little things that you may want to do and you may want to learn in order to convince you that C++ is a good thing, even for basic stuff. The C-type system is way too lax and allows for too many mistakes that, again, I've made so many times. Maybe you have as well. Did you know that in C, you can still have implicit prototypes? That is, you're still allowed to call a function without declaring it first. The compiler is going to infer a prototype from the function you call. But what if the actual function has a slightly different signature? Then this will not work in a very subtle way. Right. In C, if you have a function, if you have a pointer to integer, for instance, and you get a pointer to void, the pointer to void will naturally convert to the pointer to integer. So I can call this f function using v, which is a pointer to void. Now, who tells me that v is actually pointing to some integers? And it's big enough, it's probably aligned. No one is telling you. C will simply allow this implicit conversion to go through. And even worse, C, technically speaking, also allows you to call this f function out of a pointer to a unrelated type, such as short star. So if you have a pointer to short, you can still call f using that pointer. The compiler is going to complain typically here, telling you that the pointers are not compatible, and therefore they're going to tell you, are you really sure that you want to do this? But this is not an error. The C specification allows for this to happen, allows for you to call a function taking a pointer to integer with a pointer to a related type, such as short. And even if you get the warning here, you can easily realize what could happen. That is, you can get a pointer to short. You can convert that pointer to short into a pointer to void, and you can always do that, no warning raised, and then you can use that pointer to void to call f without a warning. So there is a direct path of conversion between a pointer to short and a pointer to int that won't even give you a warning along the way that what you're doing sounds bad. This is terrible. This can introduce so many bugs, and again, this is just C in action. C does not have a proper solid type system there. Last but not least, how many times you have accidentally mixed up arguments to a call, for instance, to memcopy? Maybe you learned that memcopy is the tool to use if you need to copy from a source buffer, which is an array of some sort of sequence of integers, to a sequence of doubles, and say, okay, let me just use memcopy to do this. Right. Now, if you do this, I have no idea what's going to happen. It's you're just overwriting doubles using the content of the integers. And this is terribly bad. And the compiler is not going to tell you anything about this call. The compiler is going to simply accept it as, okay, maybe you wanted to do this, even if it doesn't make any sense. Now, none of these shenanigans would happen in C++. Yeah. In C++, if you try to use something that you haven't declared before, that's always an error. You're not allowed to touch something that is not being declared before. Conversions between pointer types need casting operators. So if you want to convert from void star to int star, you need to insert a cast. And the cast does not actually perhaps generate any code whatsoever. The cast is there for you, human being, telling the compiler, I know what I'm doing, and I really want to change the type of this pointer from void star to int star. Because the compiler would not allow this on its own. The compiler does not trust that cast to be good enough. And if I have something like a short star and I want to convert it to an int star, then not even a cast is good enough. The type system of C++ in this context is strictly more strict than the C type system, and won't allow this thing to happen under any circumstance. And the last example that I showed you, suppose that you had some integers that you wanted to change over, that you want to copy over some doubles. You can use an algorithm to do that. There's an algorithm which is called copy and. So you pass a source, how many, and the destination. And this will do the right thing for you. That is, if your idea was to convert each integer into a double and write it into the destination output, this one line will do all the job in the best way possible. No need to deal with the type unsafe stuff. No need to double check that everything is fine. No need to remember to multiply the sides here by the sides of an integer or any of those shenanigans. Using an algorithm will provide type safety at the same or even more speed than, sorry, it's meant to be more speed than the equivalent in C. And really, last but not least, there are things today in C++ that for no reason whatsoever are not in C. It looks like the C is sabotaging your productivity, and I don't see why, but these things make my productivity go up in C++. They could be added to C in any moment, but they aren't. Even simple stuff, such as single quote to group digits into numbers, or binary literals, which, crossing fingers, are going to come into C23, but they've been around in C++ since C++14. Or even a range-based for loop, a for loop that iterates over an entire array without you having to remember, okay, let me do the division, let me divide the sides of the array by the sides of one of its elements. That's the number of entries in the array. Yeah, blah. Nobody likes that. In C++, you just write for int p into primes, and you print p. Simple as that. So in conclusion, and I believe I'm really running out of time here, C still dominates embedded development. That's true. But if you want a path forward, if you are struggling with all these little annoying stuff of C, C++ is by far the easiest path forward. And my recommendation to you here is don't just jump blindly into it. Don't just do anything because you can. There is absolutely no need to abandon all your good experience from C. Just use the C++ that makes you feel you're still under control. So adopt only what you need and when you need it. The moment you will need more, that more is there for you. It's there. You can reach it. You can use it. But don't use it for the sake of using it, because that will fall back into the myth territory. Oh, I've used templates once and have been burned. Fair enough. Don't use them then. Yep. And you can still be much more productive and create so much better code by using very simple stuff coming from C++. And yeah, finally, yeah, legends about programming languages will stay with us for a long, long time. So try to understand them for what they are. Trying to understand that every time they are appealing to a worst version of you. They're appealing to your animal instincts and telling you, okay, stay where you are, stay in the comfort zone, because that's what these legends do. They will try to reinforce your prejudices. From time to time, it's good to just look at things from a different perspective, look at things from a different angle, and maybe you will find something good in C++ for you. And that's all I have for you today. Thank you very much for listening. Christoph, you're there?
Yes. Hey, thank you, Pepper, again for the talk. And we indeed have questions for your talk. And since there's a lunch break, we still have the time to ask all of them. The first question, do you think that libs like OpenSSL and curl, which are in itself written in C, have impacted the fact that C is more popular at C++ for embedded? One can also think of the C, like the POSIX standard, for example, sometimes requiring you to go C.
Absolutely, yes. I actually do believe two things. That is, the fact that these libraries have been written in C made these libraries so popular, because C is so easy to integrate into any other programming languages out there. If you take a look at any programming language, they will always offer you an interoperability API for C, right? So you can call C functions from Python, from Rust, from Java, and so you can integrate these libraries anywhere, right? And this made these libraries so popular. Now, while if that means that this also made C programming so popular, I'm not sure if that is actually the case. I can understand why using C has been a good decision for those libraries. Indeed, well, okay, I don't know in the case of OpenSSL, given the frequent reports you get about off by one reads in some string and other things that when you look at that, you say this should have never happened in C++. If only they listened. But they certainly contribute to the fact that people want to still use C, because there are great libraries and you can use them from C. But if there is one language which has got the best C interoperability and it's not C, that language is C++, right? You don't need any intermediate layer to call into C code from C++. You can use these libraries from your C++ code just as fine. So to me, this is actually a good motivation to go to C++, because it's not that, oh God, where are all my libraries? I don't have them anymore. They're still there for you. You can still use them directly from C++.
We have another question. Do you think that these strong type features may also have an impact for kind of lazy developers? Like byte operations using pointers can be annoying with the C++ compiler. You always have to static cast. You always have to cast. isn't that too annoying? And is it maybe also a reason why people just won't go there because they're just used to having weakly typed functions?
I can see that that is a thing, but I can also not see that is it truly what you're doing the majority of the time? You're doing bit operations? Because if you are, all you really need to do is just create a function that says, set this bit or undo this bit. And that function, you do the casts that are needed, and then now you have a small package to use everywhere you want. So in practice, it won't affect your daily development. By all means, yes, C allows you to do more low-level stuff more easily. But this is a double-edged sword. It also allows you to shoot yourself in the foot more easily. By that, I'm not saying that there aren't legitimate uses for this sort of low-level bit manipulation and low-level type manipulation between, get bytes from some memory mapped register and just show them somewhere else, and that work. Perfect, but you can also do the same in C++. Just, again, package the boring code once in a function, and now you just call that function every time you need to do the low-level stuff. It may be annoying, but it's like 1 minute of annoyance and so many bugs avoided in the longer tail.
And as a last question, maybe I combine multiple questions. Do you think about using C++ for bare metal firmware applications, or do you also see use cases where you would recommend C over C++, kind of a pure C way?
Well, I do see it in case you don't have a C++ compiler, and sometimes bare metal don't have a C++ compiler at all. They might not even have a C compiler, as in a conforming C compiler. They might just stick to a subset of C. But if you do have a C++ compiler, and this is more and more the case because even bare metal are moving to things like GCC these days. They just have a custom target. They get your object and they use linker scripts to assemble an object in memory that you're going to flash onto your bare metal and run it. So if you have GCC and you have C++, I really see no reason whatsoever to not use C++ even for simple things. Even if you use C with the classes, the idea that you have a class and you have operations on that class, that is the best thing you can have rather than having to reinvent that yourself. It's just, call it syntactic sugar if you want, but why not having it if it's for free? That's at least my philosophy, right?